Good afternoon, this is Schweitzer, and we're going to do a introductory video on a chapter that's called Equilibrium versus Completion, or Completion versus Equilibrium, and give you a brief idea of what this chapter is and what to expect from this chapter. So it's called Completion versus Equilibrium. There's going to be just, again, basic ideas here, nothing that's going to be diving too much into detail. Completion is really the honors chemistry or typical chemistry version of stoichiometry. And equilibrium is just kind of another version of this stoichiometry. Again, it's purely mathematical, and technically it's kind of like one of those things when once stoichiometry clicks, then the math all works nicely and it gets relatively easy. Might take a little bit to get to that point, but putting some energy into it and backing up and making sure you understand some concepts is extremely important. If there's something that's not making sense, don't just sort of work with it. Stop, let me know, and try and find some way to clarify it so you can get a bigger, broader picture of what's going on, so you can apply these concepts to more than one situation. Because this stoichiometry starts out and it goes through all different chapters. Same thing with equilibrium. We do equilibrium, all different ideas. I guess let's just start off here with completion. What does it mean to go to completion? Again, this is our typical combustion reaction. So let's do a math example of this, because this is really what we know from regular, chemistry. So let's just say I have, let's do a example of combustion. Let's do methane. CH4 plus O2 yields carbon dioxide and water. Okay, and let's say I have 25 grams of this, and let's go with let's pick out some nicer numbers here. The molar mass of this guy is 12 plus 4, that's 16 grams per mole, and oxygen is 32 grams per mole. So let's go with, let's say we got 64 grams of this, and let's go with 8 grams of this. Alright, so our problem starts out, first thing we do is we want to get out of grams and we want to get into moles, because moles measure number of particles, and that's kind of the rate at which things are used. Along with this, you also want to have your reaction balance. So 1 carbon, 4 hydrogens, 2 times 2 is 4, and then I got oxygen, 2 and 2 is 4, so I put a 2 here. So it's a 1, 2, 1, 2. With completion, one thing that you're going to get is a limiting reactant. Now, a limiting reactant is by definition a reactant that goes to 0. Essentially, it runs out in order to stop the reaction. This thing stops process. Doesn't matter if it's a chemical process or if it's a process of making hamburgers. You run out of something, the process stops. So, to show how we get the limiting reactant, there are a couple factors. One is rate used. Again, I don't want to get too deep in this. Another one is the quantity. If you want to go ahead and so I spelled quantity wrong, just make sure you know that. Either way, if you want more information on limiting reactants, then you're going to want to go watch a video on that. But essentially, let's convert this to moles. I'm not going to show the factor label here because we picked up some nice numbers. 8 grams. 1 mole weighs 16 grams, so 8 grams is 0.5 moles. And 64 grams, 1 mole weighs 32, so this is 2 moles. Since I have more of this, but this is being used up faster, it's a possibility that this one could last longer because there's more of it, or it could run out faster because it's getting used twice as fast. This is simple proportions. You could note that it's being used up twice as fast, but I have 4 times as much. Therefore, this should outlast the methane. So at that point, you'd say, okay, well, let's run the methane down to 0. Just see, minus 0.5 down to 0. And by having a 0 here, this indicates a limiting reactant. When you go to equilibrium, you will not have a limiting reactant. That sounds strange, but that's the basic difference. This thing, losing 0.5 of this means I'm going to lose one of these guys, and I'll have one left over. And then I'll gain, at this point, I have none to begin with. I will gain, at a 1-to-1 ratio, a positive 0.5. And then I will gain, at a 1-to-2 ratio, 1. And this is how much I have in the end. This is how much I have at the beginning. Or sorry, at the end. This is how much I had in the beginning. Now, I could graph this, and it would look kind of like this. I have on a y-axis, I have my concentrations of all my pieces, and this might just be time, or the process of the reaction. And you'll know at this point I have lots of reactant and not so much product. You also note that I even still have masses here, so it's not really based off of concentration. It's more just a general size amounts that I have. I have, let's just say, this amount of oxygen, and then I have half as much, or actually a quarter as much, of the methane, CH4, and then as far as my products go, my CO2 and my H2O are both sitting at 0. So as the reaction proceeds, I start losing and gaining things based on my stoichiometric ratio. So the rate at which I'm losing my O2 would be the same rate I'm gaining my H2O. Alright, so I would be losing the O2, losing CH4, and gaining these guys. So as time progresses, my CH4 dwindles down to essentially nothing. In that time, I am losing my O2 faster. I'm going to change this to the O2. So my slope would be less. But the problem is, granted, I am losing it faster, but the CH4 runs out before I get a chance to use all my O2. At that point, my H2O and my CO2 are also being produced. I am producing the H2O at a greater rate than I am my H2O than I am my CO2. So there we go. This would be my CO2. This is my leftover O2 represented by that 1 there, and this would be the H2O. Notice that since I both started with 0 product, I end up with more H2O than CO2 in the end. In fact, twice as much. So this is your typical reaction, and then of course it just simply stops. And that is a definite characteristic of a reaction that goes to completion. Alright, so all of these details we will go through and do a handful of examples. We would spend a few weeks on this in regular chemistry, but in here we're just going to do a handful of examples and move on. So what about equilibrium? What does this mean? Well, first of all, whenever you have a reaction, we often think of some either going to completion or going to equilibrium. Now, a reaction has what we call the reactants and the products. So a reaction can move from reactants to products. That's what we just did. We call this the forward reaction. And then a product can then, in almost all cases, actually return back to the reactants quite possible. We call this the reverse reaction. Okay. Now, for a completion reaction, essentially the reactants going to products is the only process taking place. There is no reverse reaction. If there is, it's just so small that essentially it's not being practically used. So, and that way all we have is forward. But it's a possibility that maybe the reverse reaction has some viability. So now they'll start showing it reactants going to and from products. Now, I use the size of the arrow at times to emphasize, which is more prevalent, the forward or the reverse. Okay. Now, we do know that at some point concentrations of items, okay, can affect the rate of a reaction. So as a reaction takes place, we have essentially collisions of particles. So if I have a reaction in which has lots of reactants, I get lots of collisions, and therefore I get a very fast rate. As those collisions diminish, I get less and less collisions, and therefore less and less rate, and the reaction slows down. So if I have a reaction that is going from reactants to products, okay, and let's just say I'm starting out with A plus B yields C. Now I know there's a forward reaction of A and B reacting to produce C, but there is also a reverse reaction potentially where C can break apart back to A and B. So if I have a process here where essentially I have, let's say, 10 of these, and I have 20 of these, and I have 0 of these to start with, then obviously there's no C to break up. So this, even though I have it listed here, this thing is quite minimal. Okay, and let's see, let me erase this. Okay, so in that case, it just isn't there yet. I need to produce some C before that reaction starts kicking in. Okay, so in this case, I'm going to rewrite this process here, and I'll graph it here. So we have A plus B yields C, and initial conditions. I have I have a 10 A's. I have 20 B's, and I have no C's. So C would essentially be here, and A might be right here, and B might be right here. Okay, so essentially what we're going to do this thing is we're going to track concentrations. Now again, as I proceed to products, I have a very vigorous forward reaction because I have the most particles at that point that I'm going to have. But as I start dwindling in A and B, the forward reaction, I might show this, okay, these things here start to disappear at the fastest rate. Now they both have 1s here, so the slope would be the same, okay? And then, but as I lose these guys, my nice vigorous forward reaction starts to dwindle, all right? And it starts to get the point where maybe it's slowing down. And of course, as it slows down, the reverse reaction, which was inept before, is starting to pick up. And eventually, again, it's a teeter-totter process between the forward reaction and the reverse reaction. At the beginning, it was all forward reaction. The forward reaction was going like gangbusters, and the reverse was nothing. But as we start to proceed, we lose reactant and gain product. So the reverse reaction starts to pick up a little bit, and the forward reaction starts to drop off. And at some point, we tip to where they both are equal. And as they tip to being equal, we strike a balance. Where, okay, now the forward reaction is producing just enough to feed the reverse, which is making just enough backwards to feed the the reactants, and it just gets stuck in this back and forth method. We call this point equilibrium. Okay? It appears that nothing is occurring during equilibrium, but in fact, it is in fact still proceeding. It just looks like it's balanced. Again, we have a situation where the forward reaction used to be really vigorous, and in the end, they two end up balancing each other in some little static point. Now again, in this process, we have 10 of these, 20 of these, so maybe we pick up some of this guy along the process, and eventually we reach this balance point where it levels off like this. Okay. Now, in this case, we have situations where, again, we have lots of reactant here, not so much product. In this particular example, might end up being what we call reactant favored, which means that when we strike that unique balance between the forward reaction and the reverse reaction, is there more product or is there more reactant? In this case, the concentrations of our reactants, concentration A and concentration B, appear to be higher than this guy, C. So we call that reactant favored. You could easily draw a little chart out where we say, okay, well, maybe the C goes like this, and A and B end up being here. A, B, C. And now C is much higher, so we might call this product favored. Notice that none of my reactants ever strike zero. None of my products, well, they may have started at zero, but nothing goes to zero. So there's no reactant that goes to zero, therefore there's no limiting reactant. The ice table is specifically designed, we use this in stoichiometry, but really it's specifically designed for equilibrium. In this case, let's just say I lose, let's lose 2 of these guys 1 to 1. I would also lose 2 of these guys, and I would gain 2 of these guys. And in the end, or we call it equilibrium, I would have 8, I would have 18, and I would have 2. So at the point, this is my equilibrium mixture. Obviously, I have more reactant than I do product, so I am what we call reactant favored. Okay. Now, the last little bit here is we have this thing called an equilibrium constant, K. And the question might be, why do we need an equilibrium constant, and what does it do for us? Well, if a reactant goes to completion, it makes it pretty easy to figure out how much we're going to get. I mean, if we got 50, hamburgers, we could figure out that we're going to get, assuming everything else is in excess, 50 burgers. But if something doesn't go to completion, then how do we know how much actual product we're going to get? And this is where the K value comes in. Our overall goal of this thing in the end, maybe not so obvious, but our overall goal, honestly, is to figure out how much we're going to get. I mean, if the product is something we want to sell or use, how much are we going to get? We know that not everything that was original reactant will flip to products. So what are we going to get? Over time, scientists have tracked concentrations, and as they're trying to figure out, what's going on here, it turns out that in our little teeter-totter situation here, where we had, lots of reactant, the reactant was really high, and the product was maybe really low, that as time progresses, and this may take a long time for this to occur, just depends on the reaction, we lose reactant, we gain product, and we end up in some balance. Now, I drew the teeter-totter flat last time, but maybe this balance isn't flat. Okay, maybe because the flatness might represent equal amounts of both. But let's just say this thing just teeter-totters to this, okay, where we still have decent amount of reactant and still have a decent amount of product. And now we're at a static point where the forward reaction equals the reverse reaction. Okay. At that point, how much actual product is there? And does a reaction always go to the same balance point? And this is some questions that scientists were trying to figure out. If a reaction always goes to the same balance point, well, then maybe we can predict ahead of time, if we know how much of this we're going to have, how much of this. So scientists started to track concentrations. And they figured out that at a particular temperature, that it appeared that reactions were forming a relationship between the reactants and the products, some sort of a balancing act between the two, and that a particular reaction will always have the same relationship between product and reactant. This relationship, and it actually had to do with the concentrations of the products and the concentrations of the reactants, and that is actually fairly important in that since we are tracking concentrations, brackets mean molarity, we are tracking concentrations, that things that didn't have or don't have a concentration, they don't really affect equilibrium, meaning that pure solids and liquids, okay, they do not have a concentration. What's the concentration of water? It's just based on its density. It never changes. So in this case, since we're tracking concentrations, pure substances do not affect equilibrium. We'll see a lot of ways in nature where that really does work. It doesn't really change anything. So in this sense, we have a relationship between the ratio of products over the ratio of reactants, and this balance numerically forms a constant which is called K. And K, in the end, will allow us to know to what extent a reaction goes to product or goes to reactant. Larger Ks mean more product. So we call them product favored. A smaller K is one where, well, we mostly have denominator here and not so much, product. We'll have to have some, likely, but not much. So in this case, this is going to be, we call reactant favored. And we'll spend basically the rest of the time sort of trying to track the fact that if we know a K value and we know how much we're starting with reactants wise, or we know how much product we have, we can figure out the ratio and figure out how much product there'll actually be. It's just a math problem at this point. And that's going to be our general introduction to equilibrium. Let's just take a moment here and let's just talk about a few of the different types of equilibrium. We really don't deal with that many types of equilibrium, although they literally are everywhere. The basic types that we will deal strictly on, one is solubility. Now, again, anytime you have an equilibrium, you have two processes that are competing back and forth against each other. In this case, we have a forward reaction with a reverse reaction, but really it could be spending money versus saving money. It could be people entering a city versus people leaving a city. It could be political trends, people moving to the left, people moving to the right, how people voting. So it is just anything. Equilibrium is everywhere. The Earth gaining heat, losing heat. So some people think that global warming is just a equilibrium situation. Either way, so solubility is one of them. And the way I draw that picture out, got my beaker and got some water in here. I have a solid that's going on the bottom. That would be required. And if there's solid on the bottom, you know that my solution is maximized. It is in max solubility. It doesn't have to be very soluble, but it's to its max. And at this point, would still, even though it appears that nothing's happening, we still have things exiting the system and things entering the system as far as solubility is concerned. These are my two competing processes. Another one might be vapor pressure. And I can just close this off for now and just to make the example easier. Close the top. We got ourselves a liquid, and it could even be H2O. As it evaporates, we get lots of little water molecules flying in here, and then eventually we reach an equilibrium where things are exiting the system and things are re-entering. And this pressure above here is called vapor pressure. Other ones we might have is just a general reaction between, let's just say, in a gaseous phase, or it could be in a liquid phase, circles going back and forth to, let's say, squares. So in the system, it could be in liquid, it could be in gas, circles, squares, squares, circles, 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 circles. So in this case, I got lots of circles, not so many squares. If I'm at the balance point, this is reactant favored. So this is your typical reaction that simply bounces back and forth between a reactant and a product. Another example of this type of situation really is your acid-base reaction, where we have, let's say, unknown acid HX reacts with water to produce H3O plus ions and X negative, and the reverse reaction would go back. So in this case, we have reactants and products flipping back and forth. Now this would be in the liquid phase, but we could also have other examples which are in the gas phase. So really our main units of concentration of tracking these things are either going to be in moles per liter. So anything that's got a moles per liter can be tracked, or even in gases, we can track things in what's called atmospheres or in pressures. This would be partial pressures. So this really isn't a lot of different types of equilibrium that we would essentially be looking at. And we'll stop there. Thank you very much.